In this video, I want to go over the different instructions that we can use in our AT-Robots assembly language programs. You'll need to understand them to write your own programs, and you'll need to understand them to read existing programs. Another thing that we need to know is about the timing of the different instructions. So we need to know how long it takes to execute a particular type of instruction. For an awful lot of the instructions, they can complete in a single clock cycle. But there are other instructions that may take longer because they involve a more complicated operation, or they may even be somewhat undefined because they involve external systems or devices of some kind. So let's get to looking at these. So there are two slides in the presentation I prepared for you and placed in that AT-Robot zip file that I provided through the class website. And I'll go through them now. Both of them are organized the same way. There's in the major column a description and syntax for each of the instructions. The name of the instructions is in the central column, and then to the left is the timing of that instruction in terms of clock cycles of the AT-Robot CPU. As we look through these instructions, and in particular as we look at the syntax, there are a couple shorthands that show up, two shorthands really, that we need to understand. The shorthands here are for these concepts V and N. So this line here, oops, I guess I can't select the whole line, but for the add instruction, we can see that the syntax is add V N. And as I mentioned in a previous video, I would typically put a comma between these two arguments. And what that does is it finds the sum V plus N, and then it stores the result into the left operator, left operand V. So both V and N end up being inputs to the arithmetic, but the output, the calculated result, gets stored back into V. So what's the V and N mean? Well, V is short for variable and N is short for number. And the real differentiating factor is that a number can be more things than a variable. So variables include things like, they're not just variables as in I declared a variable called whatever. So when we see the V here, it means more something like variant. So it's a thing whose value can change. So that could be a register, so you can change the value of a register. It could be a variable that's in a memory location, so that value could change. It could be a reference done by a pointer, let's say, by providing a memory address. So the address itself isn't changing, but what's at that address can change. This is in contrast to what a number is. So a number can be all the same things that the V can be, the variant capacity, because you can get numbers out of all those things whose value varies. But what you can also have are things like straight up immediate numbers, like a 15. So that distinction is important because if we're going to take V and N and add them together and store the result back into V, what V cannot be is the number 15, because how do you add 4 to 15 to get 19 but then store the result of 19 into 15, right? So V is a thing whose value can vary. N is a thing that has a number in it. It could be something that could vary, but it could just be a standalone number. Once we understand that, we're really set to look at the rest of these instructions pretty quickly. Excuse me. The first instruction is the no-op instruction. It performs no operation at all. It just wastes a clock cycle. And that's useful for timing or adding some kind of delay that you might need. Now, as you improve your skills in AT-Robot programming, you'll probably decide that you don't like ever having clock cycles go by where you're not doing something. So where you would otherwise be wasting cycles to make sure there was enough time between two critical events, you could fill that time with partial calculations for something you were going to do later anyway. But the no-op instruction is common to all platforms out there, and so it's one of the first instructions we see. The next set of instructions are arithmetic instructions, so addition and subtraction. Then we have effectively shorthand instructions, although they do have unique values. We have the increment instruction, which just takes a single variant value and adds 1 to it, and the decrement instruction. So both are like add and subtract, but we don't have to provide the second argument of 1. And these make assembly code much cleaner to use. So if you're going to add 1 to something, don't say add to ax 1. Instead, say increment ax. The reason for this is because there's an awful lot of basic constructs. Think loops as an example, modifying the sentinel value of a loop, where you just need to increment that sentinel variable or decrement that sentinel variable. In such situations, actually writing out the full code that says we're going to do addition and you need to read this other parameter to find out how much we're adding causes the person who's reading that code to put their mind in a different cognitive place, because they're looking to interpret why are we adding whatever it is we're adding. Whereas when we see an increment or a decrement, we tend to understand that those are parts of processes that are moving through things linearly. And so it makes it much easier for us when we see increment or decrement to more correctly interpret what that code is for, which means we'll be less likely to introduce defects as a side effect of how we've read that code. So please use them. So addition, subtraction, increment, decrement. Then we have some bit operators. We can shift a bit pattern to the left, and when we do, we'll provide the value that we're going to shift here in V, and N is the number of bit positions that we want to shift it. We can also shift to the right, and the arguments work the same way. Similar to shifts, we can do rotations to the left and to the right. Now when we do these shifts up here, the SHL and the SHR, these effectively work as unsigned shifts. So it just slides the bit patterns one way or the other, and in the vacuum left behind from the shift, we'll insert zeros to those positions. However, if you wanted to use sign extension or do shifting for the purpose of mathematics, like say shifting numbers to the left, because that's the same thing as doing multiplication by some power of 2, to make your code more readable, you prefer to use, or we prefer generally to use, the arithmetic shift operator. So shift arithmetic left or shift arithmetic right. They're fundamentally the same as the other shifts. The difference is they're working as signed numbers. Now, shifting to the left arithmetically is exactly the same as shifting to the left just bitwise. But shifting to the right is different. So when we shift to the right, there's a difference between an unsigned shift, which has the H in the middle for shift to the right, and an arithmetic one, shift arithmetic right. When you do shift arithmetic right, you shift to the right, but you fill the vacuum with whatever the original sign bit was, so you sign extend. That means that we're effectively doing division by powers of 2. Now, if shift arithmetic left and shift left do exactly the same thing, why choose one over the other? Well, if you're shifting left to do multiplication quickly, then you want to do shift arithmetic left, because anyone who reads that code will understand you're not manipulating a bit mask, you're doing arithmetic. Okay. Further instructions include negation. This is a one parameter or one argument instruction. You tell it which variant value to negate, and it stores the negated value back into that same location. You can also do some bitwise logic. There's OR, ANDing, and exclusive ORing, as well as inversion through the NOT instruction. We can do multiplication and division with multiply for, or MPY for multiply, div and mod for doing integer division where we want, in the case of div, the quotient, and in the case of mod, the remainder. Please note that for all three of these, for multiplication, division, and modular division, the actual CPU time on these is 10 cycles each. So these are relatively expensive operations. If you can avoid using them by doing some kind of fancy shifts, or even just adding several times. You want to multiply something by 3. If you add it to itself somewhere 3 times, that'll take 3 clock cycles instead of 10. So you can leverage the concepts, writing the multiply, the div, and the mod in your code at first, and then you can improve the performance by decreasing the CPU time and replacing those as needed with something a little more clever. We also have call and return instructions. Here's a call. So that's used for calling functions by identifying a label that we want to go run as if it were a function. And at the end of those functions, we'll use a return instruction, which will take us back out of the function that we called, which is just code, and take you back to the line after the most recent place that called that function. There is a jump instruction, which we've mentioned before in other presentations, shorthanded as JMP, and that will blindly take you to whatever label or address you provide, whether it's a bang label with an exclamation point or a calculated numeric label. So we just provide the target and it jumps there unconditionally. If we want to go somewhere else in the code, but based on some kind of condition, say for an if statement or the condition of some sort of loop, then we'll typically start off by executing a comparison instruction. For this, we have to provide 2 things that are numbers. There's no storage involved, so there's no variance in there as arguments. It compares the 2 numbers and then sets the 4 bits of the flag register appropriately based on the comparison. From there, we then use a conditional jump instruction to determine when we should change the execution flow of our program and go somewhere else rather than just run the next instruction down. So in the second slide of instructions, we lead off with all of these. So we've got JLS, and you should internalize sort of what each of these mnemonics means. So this is jump if the less than flag is set. JGR, jump if the greater than flag is set. JNE is jump if the equal flag is not set, or typically we would say jump not equal, but it means if the equal flag has a 0 in it. JE is jump equal, jump if the equal flag has a 1 in it. JGE is jump greater than or equal, so if either the greater than or the equal flag have a 1, we will jump to the other location. Otherwise, we just run the next instruction. JLE is jump less than or equal. Same concept. If the less than or the equal flag are set, then we take the jump. But that's only going to happen if we compare this thing to that thing, and the thing on the left happens to be less than or equal to the thing on the right. And so it becomes fairly straightforward. JZ is jump if the 0 flag is set, or jump if the result was 0. JNZ, jump if the result was not 0, or the 0 flag is not set. JTL means jump to line, but I totally recommend you forget this instruction exists. I mention it because it's officially there, but generally speaking, there's no good reason to use this that I am aware of. When you say jump to the nth compiled line of code, that means that you know specifically what the nth line of code is. And if you ever wrote a line of code above it or deleted a line of code above it, then you have problems because the code you originally intended to run has changed which compiled line number it exists on. So generally speaking, do not plan to use that particular instruction. If you come up with a really clever reason to use it, let me know. I'm interested. There's an exchange instruction. The exchange instruction effectively does the 3-point swap that everyone learns to program early on, where you take A and back it up into a temp variable, and then you clobber A with B, and then you restore the original value of A from the temp variable down into B, and now A and B are swapped. The exchange instruction just does exactly the same thing. It just uses a special memory location that's internal to the CPU behind the scenes, so that you don't have to write the 3 lines of code. But if you look at its timing, you'll notice that it actually takes 3 cycles, just as if you would have written the 3 lines of code. So you can use fewer lines of code to get the same task done, but it costs the same amount of time. The next instruction comes in a pair. The do and the loop instruction are designed to work together. The do instruction, you provide a number to, and it does nothing more than set the CX register to have that value in it. But it reads do, let's say, 5. And then the loop instruction takes the CX register, decrements it by 1, and then checks to see whether or not it is 0. And as long as the CX value is still greater than 0, it will jump to whatever label you provide to it. So it says loop to n a number, but what you really provide here is a label. So a bang, just like the conditional jumps or the regular jump, or a calculated numeric label. So they both do and loop work off the CX register. One basically initializing the sentinel variable CX for how many times you want to loop. So if you say do 5, it means do this loop 5 times. When you get to the bottom, you loop back to the top. Not to where the do instruction is, but just after that. In this way, the code will repeat itself 5 times, because you'll have to decrement CX 5 times for it to get down to 0, which is the first number at which the loop instruction doesn't take the jump. You can do all of that without either of these instructions, but they absolutely make the code easier to read because it's clear you're intending to do a post-sentinel loop, a do while, rather than a pre-sentinel like a while loop. So that's what they're there for. The test instruction is one that we already talked about. It effectively does the bitwise AND operation, the binary AND operation, but it doesn't store the results. It just stores the flags. The move instruction we've talked about before, but the move instruction effectively just copies a value from one place into another place. The address instruction lets you determine the excuse me, the memory location of something else. So if I were, this is also a good example of some discontinuity in the documentation. So there's an instruction ADDR, the address instruction, but it's the same thing as the location instruction, LOC. They're 2 different mnemonics for the exact same operation number, and so they do everything exactly the same. It's really just whichever you prefer. I try to stick to all the things that are in the name column because those are the ones I see most commonly. But if you were to say address x, let's say we have a variable x comma y, then what you're going to do is find out the memory location of y and store it into x. That'll allow you to use x as a reference later on. And this is good for things like arrays or something similar. Get sets the first argument to whatever is in the second argument from a memory location at that second argument. I very rarely see this used because you can do this also, or basically the equivalent of that happens almost all the time through the move instruction, although this one makes it seem like the get is different because it's taking the memory location provided by the second variable and then referencing it. We can also do that with a bracket notation and the move instruction. I'll show you that in a later video, but I don't use get myself just because I find it confusing because it's so similar to move. Put, very similar. Put sets one memory location to the value of another, and it's the same thing as move. So I don't ever use these. Plus, they take 2 clock cycles instead of 1 clock cycle for move. So I don't like them. The interrupt instruction. This executes a particular interrupt, and you have to put the interrupt parameter sometimes into the AX register. So it depends on which interrupt number you're calling. You want to call interrupt 17, you might just say int 17. More often than not, though, we won't want to say 17. We'll want to use some kind of identifier that's predefined, so it's easier to read which interrupt that is. I'll show you those too in another video. Notice, however, that the interrupt instruction has a question mark for the time in cycles. That's because it depends on what you ask the operating system to do. So when you ask for one function of the operating system, it might take 3 clock cycles. When you ask a different instruction or a different operation to be performed, it could take 40 clock cycles. Depends on the thing you ask. So we, in a later video, need to look at all of the different interrupt functions that we can call to be able to determine how long it will take when we call, say, the location interrupt. Then we've got the input from a port and output from a port instructions. You can also say in or out. I prefer IPO and OPO for no other reason than I like to say IPO and OPO. I think they sound fun. So those are the ones that I use. When you get input from a device via a particular port number, or you send output to a particular device via a particular port, notice that the timing on those is 4 cycles plus. So the IPO and OPO instructions by themselves take 4 clock cycles. But you also have to add on to it the cost and time associated with the particular device that you're communicating to. So some devices take no extra time, and others may take 20 extra cycles. So you have to be cognizant of the port performance time as well as the IPO and OPO instruction times. The DEL instruction, that's short for delay. You give this a number and it wastes that many clock cycles. It's basically equivalent to writing no op several times in a row. But if you needed to delay, say, 30 cycles, it would be really unusual in your program to have 30 no ops, one after another, after another, after another, after another. So instead we use the delay instruction. That's the only reason it has a question mark for its timing, because how long it takes is literally dependent on the parameter you provided. The stack operations push and pop are here. So push adds something to the top of the stack. Pop removes the top thing from the stack and stores it in the location provided. The final instruction is the error instruction. This is one of the original ways you could do some basic debugging with AT robots. You get to some particular point in your program and you want to provide you, the viewer of the program, some kind of information about what's happening. You could execute the error instruction and provide it a value, and that will show up as a hexadecimal value up in the status area of your robot, or whatever robot is executing that function. It'll also make a beep if you have sound activated. So you can print a number, and when you see the 3, you'll know you're in the code where you print the number 3. Maybe you're calculating something and you're trying to print the result, and so that's another way to see it. There are fancier ways to debug at this point. Since AT Robots version 2.10, there has been an integration of a debugger, which I wrote back in the 90s, late 90s, under the moniker Fifi LaRue. And you'll see a bunch of robots in the directory who are authored by Fifi. That was just my character at the time for playing the game. Notice that the error instruction takes 0 clock cycles. So one nice thing about using this for debugging purposes is you can get a value out really quick and you can see what's going on. But presenting that value to your status region through the error instruction doesn't take up any CPU time. And so when you do it, when you insert one into your code, it doesn't interfere with the performance of your code. Now the fact that the error instruction takes 0 clock cycles, as well as, if you look up here, the conditional jump statements, all of those take 0 clock cycles as well. The 0 timing is documented by Ed Toten on these instructions because he didn't want to dissuade folks from making complicated sequences of jumps for interesting logic. But it is worth noting that because some instructions, the conditional jumps and the error instruction, take no clock cycles at all, it would be theoretically possible to create some kind of a loop structure that was effectively infinite, but didn't use any time, and thereby would bring the entire simulation to a complete halt. There is a safeguard for this in AT robots. Basically, if 20 if 20 zero cycle instructions are executed in a row, then that just gets treated as it's consumed now 1 clock cycle of time. So it will actually end up using CPU time if you try to abuse this to bring the game to some kind of screeching halt. So it won't bring it to a halt, and your robot will move forward in time. All right. To end this off, I want to look at how we actually use all those different jump instructions we saw. There was the unconditional jump, JMP, which just goes to another place in the code, backwards or forwards, up or down in your file. And then there's all those conditional jumps, jump not equal, jump less than or equal, jump greater than, etc. And there are multiple types of labels. We've got 2 labels. The ones that start with the exclamation point, where we name the label, and the ones that have a colon in front and then a number. These are the calculated numeric labels. So I've prepared a really simplistic program that we can walk through together to understand how the flow of an assembly program that has labels and different types of jumps in it would actually work. So at the top of this program, we define the variable unicorn. And then immediately we put the number 12 into that variable. So 12 is in unicorn. Now we got a label which doesn't do anything, but this label, number 12, is associated forevermore with the move AX 0 code. So move into AX the number 0. So that's what we're going to do now. So we put a 0 into AX, and then in the next line of code, we put a 3 into the BX register. So AX has 0, BX has 3. Then we have 2 labels in a row, but both labels are equivalent to the comparison instruction here. They're fundamentally one and the same. I'm making a little note for myself of what's in the AX and BX registers right now. AX has 0 and BX has 3, just so I don't forget as I go through. So we'll compare what's in the AX register to 4. Right now it's a 0, so 0 is less than 4. That means the less than flag will be set, and all the other flags will be 0. So this line of code then says jump if the equal flag is set, or more colloquially, jump if AX is equal to 4. It is not, so we won't go to the end of the code. Instead, we'll just run the next line. So we'll add 1 to AX, and so now AX goes from 0 to 1. And then we'll jump to whatever line of code is associated with the number in BX. BX has the number 3. Here is a label that's a numeric label with the number 3, so this is where we're going to jump. So we come from here up to the comparison statement again. So compare AX to 4. AX has a 1 in it, and the next line of code will jump down here to end if AX was equal to 4. So 1 does not equal 4, so we're not going to take this jump because the equal flag won't be set. We'll fall through and add 1 to AX. Now, realizing I should have made this say increment AX. Oops. So add 1 to AX, and AX goes up from 1 to a 2. And then we'll jump to BX, which still contains the number 3. Nowhere in the code so far have we changed 3 since we, or changed BX since we put a 3 in it. So we jump back here, check about the relationship between the number 2, which is in AX, and 4. They are not equal, so we won't jump to the end. We'll add 1 to AX, and that'll bring it up to 3. Then we'll jump to bx. Bx currently contains a 3, so we'll jump up here to the numeric label 3 again. Now we'll compare ax to 4. Ax has a 3 in it, so they're not equal, so we won't jump if they were equal, because they're not. And we'll go to the next line of code. Add 1 to ax, and it goes from 3 to 4, the moment we've all been waiting for. And then we jump back to the contents of bx, which is the number 3, boom, up to label number 3. Compare ax to 4. So now ax has the number 4 in it, so we're checking the relationship between the number 4 and the number 4. And they are equal, so the equal flag will be set. Therefore, this conditional jump will jump if ax is equal to 4, or if the equal flag is set, to the label called n. So now we're going to skip past the addition and the jump instruction here all the way down to n. After which we run the next line of code that follows, which jumps unconditionally to whatever the contents of unicorn is. So currently the variable unicorn has the number 12 in it because it's the first active line of code we did. So we're going to jump from here to whatever numeric label has a 12 in it, which is this thing right here. And then we repeat the whole process again. So this code is clearly an infinite loop. But the point of it is we can see how we can calculate values to jump to numeric labels. And we can do that kind of jumping either because we've got to calculate a value in a register, like bx in this particular example, or like the contents of a variable, like unicorn, right? So the unicorn variable contained the number 12 and we jump to there. In other circumstances, we jump to labels directly by name. That's the most common way we're going to see our jumps. And we're going to see them in the two major forms, the unconditional jump, where we just say go over to this code no matter what, or a conditional jump, like the jump equals down here, where we're comparing whether ax is equal to 4 or not. And if it is, then we branch down to the end. These are the major instructions, or these are all of the instructions now that we've gone through for the AT robot assembly. We've looked at their timings, and we've also looked at the way we can utilize those jump and conditional jump instructions to make the execution of our code move around so that we can do the equivalent of things like if statements and forms of looping.